shore. And that's because as the waves go into shallower water, they slow down, and when they slow down, they refract. And when they refract, they bend, right? Have you ever wondered that? I don't know. Why are the waves always coming straight in when the wind is from the south? Well, it's because they refract. They go straight into the shore like that. Right? It works both ways. So if you are above the water, it'll bend into the water. But if you are shining from below the water, it will speed up. The right side will speed up first, and that will make it bend back that way. They'll retrace their paths like that. Yeah, okay. Just get a flashlight and get under. I've actually done this. Okay. You can see, when you see from down here, what do you see? When you look that way, you're actually seeing stuff from there, right? When you look at some edge here, right, you're actually seeing stuff that's right along the water line. Yeah? You ever wonder how fish can see you so well? It's because they've got kind of literally a fisheye sort of view of everything, right? They're seeing stuff right on the shore. You can be down low at the edge of the water, and your light is skimming across and diving into the water there, and they can see you. Yeah? They're smart too. I've tried to catch, like, salmon in streams, right? I've tried to, like, sneak up on them. No, there's no sneaking up on them. They'll see you. Okay. Here he is waving to the attractive woman like that. Okay. This is, when people are standing in water, they look shorter than they really are, don't they? This is why, because the light from her foot is coming up like this, and it's bending over. Well, of course, the person, your eye doesn't go, oh, that is a refractive property, so therefore I must project her image of her feet much lower than they really are. No, he's looking at her and saying, for though she is attractive, her legs are of such a proportion that she would not be a good bearer of my child, okay, or something like that. That's right. He is saying something like that about her, right? For though she is attractive, she has feet where her knees should be. And therefore, I'm going to be casual. I don't know. Okay, so what we have to do is derive a formula. So this is a very beautiful picture here, isn't it? Isn't that a beautiful picture? We're about to make it uglier. So let's make this uglier. I know, I'm sorry. But I'm going to do it in blue, which will make it somehow better. I'm going to do this in the name of science. Such a beautiful picture. Now, I am going to draw a line right here. And I'm going to do that because I need to draw a line right there. Okay? Now, this is a right angle here. This is also a right angle. Don't you see that I've got two right triangles here? And these triangles are co-hypotenusular. They are two co-hypotenusular triangles. That is a word that they never taught you in math class, did they? That means they have the same hypotenuse, don't they? Yeah. This is the wavelength in this medium. I'm going to call this lambda 1. This thing here is the lambda in the other medium. Yeah? Okay? They both share the same hypotenuse, which is right here. Right? Okay? And then I think this angle and this angle here are congruent. Aren't they? I think they are. Can I prove that? How would I prove that? Oh, I know how to do it. This angle and this angle are complementary. Yeah? And this angle and this angle are complementary. Yes? This because it's in a triangle. This because it's just the other part of the angle, right? So therefore, angles that are complementary to the same angle are therefore congruent. Yes? Mr. Capacious. All right. This angle here and this angle here are also congruent. Can I prove that? Is that harder? Bless you. How do you prove that? I think it's the same though. I'm going to call it theta 1. Then we got a proof for that. I'll just move on if I don't. I'll call that theta 2. Those angles have to be congruent because why? Let's do the same thing. It's complementary to that angle, Is that angle and this angle, are these guys? These are the same angle, but how do we prove that? I don't know. I'm gonna pass on the geometry. It'll occur to me at some point, you know. Okay, but these guys are this angle and that angle are congruent. This angle and that angle are congruent, right? And so now we've got a relationship. Okay. I know that theta 1 is opposite over hypotenuse, right? And the opposite is lambda 1, right? And then it's over the sine of theta 1, sorry, is the opposite side, which is lambda 1, right, divided by the hypotenuse. Okay? And then I know that the sine of theta 2 is lambda 2 over the hypotenuse. Nobody's got that geometric proof yet? Let's do. Well, can we do supplements? Theta 1. I don't know. I know it's true. Can't prove it. That works. Isn't this true, though? I'm just using sine as opposite over hypotenuse, right? And then I want to divide these guys. And then just for fun, I'm going to say that lambda 1 is the velocity of medium 1 times the period of the wave. Just because I feel like it. I feel like making things cancel out, right? And then I'm going to say that lambda 2 is the velocity of medium 2 times the period over the hypotenuse, right? And then this is beautiful. Isn't the period the same if the frequency is the same? Yeah. Yeah? Isn't the hypotenuse the same? They are co-hypotenicular. So we get sine theta 1 over sine theta 2, and this is in the data packet, equals V1 over V2. This is not Snell's law. This is like the IB formula that they give in the packet that nobody else in the world uses that I know of, right? And then the real formula is with Snell's law is actually different. So I'm going to recast this. A velocity, if n is c over v, right, then v is c over n, right? So that is c over n1, the index of refraction of this medium, right? Index of refraction of this medium, right? C over n2. Well, that's not so pretty, right? That equals n2 over n1. Yeah, doesn't it? Because the c's go away, and 1 over n1 over 1 over n2 is just the reciprocal of the, yeah? That's true. And then if I cross multiply this, we'll get Snell's law the way the world writes it and your book writes it. n1 sine theta 1 equals n2 sine theta 2. Yeah? This is Snell's law, not Smell's law. I replaced them with the speed of light divided by the index of refraction. Because nobody, by the way, gives the speed of light in a certain medium. They always give the index of refraction, right? So the formulas in your data packet are, let's see. Here are the formulas in the data packet in the very wrong way that IB writes them, in my opinion. Okay, they write it this way: n1 over n2 equals sine theta 2 over sine theta 1 equals, and then you're going to use one of these or the other, right? This is the way that IB writes it, and I can't change what's in the data packet, so there it is, right? This is the way the rest of the world writes it. Yeah? They will give you problems where they give you the velocity. So you're either going to use this or this, and the rest of the world does that.